Just going on. After 5 seconds, you may start, Dr. Prashant.
Okay, yeah. Yeah.
Yes, you may start.
Okay, thank you, sir.
Okay, so hello, good morning to all. I, Dr. Ashok Kumar, Assistant Professor, Department of Physics, Central University of Punjab. I would like to welcome you all on the behalf of Central University of Punjab and Department of Physics on this occasion of Foundation Week celebrations of our university. As a part of Foundation Week celebrations from 21st February to 28th February, and under the dynamic guidance of our Honorable Vice Chancellor, Professor Raghavendra P. Tiwari sir, Central University of Punjab is organizing a special webinar series by eminent speakers in various fields. In this connection, we have with us one such eminent speaker, Dr. B.B. Kale, Director General, Center for Materials for Electronics Technology, Ministry of Electronics and Information Technology, Government of India. I heartily welcome you, sir. As a custom of our university, we start any program with university anthem. So I would like to request all the dignitaries and participants to rise for the university anthem.
पंजाब केंद्रीय विश्वविद्यालय, पंजाब केंद्रीय विश्वविद्यालय, संस्कृतियों का मिलन बिंदु, विज्ञान दृष्टि धारण करके विद्या की इस फुलवारी से महके देश का प्रांगण सारा, ज्ञान विज्ञान का मधुर संगम, जीवन मूल्यों का सहारा, ये नवाचार का पाठ पढ़ाता, देश विदेश की समझ बढ़ाता, भावी पीढ़ी का ये निर्माता, विश्व बंधुत्व का भाव सिखाता। तेरी शान रहे, तेरा मान रहे, पंजाब केंद्रीय विश्वविद्यालय, पंजाब केंद्रीय विश्वविद्यालय।
In emerging semiconductor engineering. Before introducing the speaker, let me briefly introduce about our university and department. After established in 2009 by the Act of Parliament, Central University of Punjab is one of the fastest growing university with NAC A grade and is only newly established university, Central University in top 100 NIRF ranking. Department of Physics is started in 2013 and currently running master's and PhD program and having 8 faculty members. Faculty of the department are involved in high quality research in thrust areas. Since last 5 years, faculty members have published more than 100 research papers in international high impact journals of repute. Under the dynamic guidance of our Honorable Vice Chancellor, sir, our department is achieving new milestones. Now, I would like to invite Dr. Prashant S. Alegaonkar, Associate Professor and Head of the Department of Physics, to formally introduce the today's speaker of the webinar. Dr. Alegaonkar.
Thank you, Dr. Ashok Kumar. Thank you for your nice introduction. Good morning, Kale sir. Good morning, all of you. Today's speaker is very special to us, Dr. Bharat Kale sir. I know him for last 25 years. He is currently holding the position of Director General, Center for Materials for Electronic Technology, CMET, who was founded by him. He is physical chemist and completed his PhD from Council of Scientific and Industrial Research, National Chemical Laboratory, under the guidance of Dr. B.D. Kulkarni, Chemical Engineering Division. He is expert in widespread areas: nanostructured advanced material, photonic crystals, photonic materials, solar cells, and thermoelectric, solar cell, lithium-ion batteries, lithium-ion dry batteries, energy materials, hydrogen production from semiconductors, and so on and so forth. So he is a material chemist, and his Google index is H index is 46, and he is having more than 270 papers of international repute. He is having 22 patents, 4 more US patent he is applied for, and he has so many PhD graduated under him. More than 20 people graduated under him, pursued for PhD and successfully graduated. He is having more than 25 students for MTech dissertation, MTech MSc dissertation, and he has handled number of projects, more than 20 projects he handled, and with a budget of more than 18 to 20 crores from MEIT, DST, BRNS, ISRO, and in addition to this, he is having number of international projects with UK, Slovenia, Japan. He is having large number of collaboration all over the world. He is a recipient of Vasvik International Research Award. He is a fellow of Royal Society of Chemistry, and he is a fellow of Indian Chemical Society of India. And then he is a Asia Pacific Academy of Materials. He is a recipient of Asia Pacific Academy of Materials 2019. With this, I warmly welcome Dr. Kale sir, and we are here to, we are eager to have talk from you. Our YouTube is live, and we are lively streaming. Our all participants are connected through YouTube. So welcome, sir.
Thank you, Dr. Professor Ali Gaukar, and thanks to Honorable Vice Chancellor Tiwari and other staff members of the university. Thanks for giving me the opportunity to share our research ideas, our research work which we are doing here in CIMET, basically in electronic materials, which will be really helpful to the all disciplines of the university. So today I'm going to talk on some unique nanostructures and some very typical systems now we develop, like quantum dots in glasses. And today I'm going to talk only one application, like hydrogen, because hydrogen is a future fuel now, and we should understand that how this hydrogen can be utilized for future as a fuel, which is a very it's a very lightweight. Hydrogen is a lightweight, and the calorific value of the hydrogen is extremely high, and it can be used for high power automotive applications. So in the talk, I'm just stress on the hierarchical nanostructures, then some doped nanostructure like nitrogen doped nanostructures, how this is useful in the hydrogen production. Then quantum dot glasses, which are unique systems which we develop in our laboratory. It's not, if you can see the Google and all this, only our papers will come in this area. So I would like to introduce these systems to the students, so that how these quantum dots are really helping in the glasses also for their different applications. Let me introduce my laboratory. Now I'm the heading of these 3 laboratories in the Center for Materials for Electronics Technology, which is under Ministry of Electronics and Information Technology. It is not under the CSIR or DST, but it's in the Ministry of Electronics and Information Technology. So we have 3 laboratories. We have Pune lab, where we work on high purity materials, electronic for space applications, all electronic applications we covered, where we have polymers, glasses, then organic materials, inorganic materials for electronic application. In Trichur, we have a ceramics for electronic, because a lot of ceramics are used in electronic systems like substrate, aluminum nitride substrates, alumina substrates, or some doped substrates. So this kind of ceramics, glass ceramics, are we work on this area. We are working in the Trichur laboratory. In Hyderabad laboratory, we are working very high purity metals and alloys because many semiconductors, very high purity semiconductor metals like you can see that cadmium, mercury, gallium, indium, zinc. We require almost 7N to 9N purity, 99.99 is 4N purity. Like that, we go up to 12N purity in our Hyderabad laboratory. We have a state-of-art facility there. So then some of the things are required in the for the space applications and for DRDO applications. We do there, like in hafnium. Hafnium is a very rare metal, but it is used in the nozzles of the nozzles of the rocket, where the propellant is fed. Their temperature goes to 3000 degrees centigrade to attain at this temperature. Only alloys are useful because the alloys gives the melting temperature maybe 3500 or 4000 degrees centigrade. So alloy of zirconia, titanium, and hafnium are used in this system, in this nozzle. And hafnium, we require almost 320 kg hafnium every year. So we have a small pilot plant there. We produce and we are giving to ISRO for the satellite. Every year we are sending so many satellites. So in the production of satellites and in the production of launching vehicles like rockets, these materials are. Apart from this, recently we had the center of excellences, because center of excellences are needed today, is a need of the country, because through this center of excellences we can help the industries, because we may not have the technology, but this whenever we are buying the technology from the outside, or we can develop our own technology, but the support to these technologies for the manufacturers required for at the end, or and they require the continuous support in the advancement of this technology. So these things are very important. So we established four center of excellences. Like one is the rechargeable batteries and technologies, where we have lithium, sodium, all kind of batteries we work, all kind of chemistry we work here. And this is partly supported by industry. Almost 40% is from the industry and 60% from my team. Then additive manufacturing, where 3D printing, now 3D printing has come in the market. 3D printers, you might have seen, like polymer based. We can have all kind of designs in the polymers material. But we need to work on the small components of the electronics, where some composites are required, when ceramics are required, or metals are required. Or in vehicle, some of the part of the vehicle also we can do with the metal 3D printing. This is very essential. Now you can see that if you see the news now today, we are there are houses people are making through the 3D printing. So small houses of 500 to 1000 square feet. It's possible to construct within 24 hours. So any kind of design, you can have designs in rooms, you can designs in outside design, inside design, everything we do. Because whatever maybe we are giving the feeding at the computer, same design we are making in the house. So that kind of house we can have. So many things are happening in this 3D printing. So we would like to utilize this center, where we can have the components in the optical components, then electronic component systems, then design of the 3D printer according to the process, which is very important. So we have also industry involved in that. So industry is going to fabricate the 3D printers as per the process. Suppose your process is you want to make a substrate of any kind of substrate. So we need a lot of process in which there is a sintering, there is a calcination, sintering, shrinking, everything we do in the one process, in the one through this attachment to these 3D printers. So this kind of one 3D printer, we can have all this process, and we can have the small components or the bigger components. The advantage is the 3D printer is cost doesn't means cost is not a matter for whether a single atom we produce or 30 atoms. So that is the advantage. Only that constraint is how we can increase the production through this 3D printing. That is very important. E-waste recycling and management. E-waste recycling is very, very important today because everybody is producing e-waste every year. So if you not control this, you will not recycle it. So you will see after 20 years mountains of the e-waste. Okay, so this e-waste recycling we do in Cement Hyderabad under Center of Excellence. We develop technology of 500 kg and 1 ton capacity pilot plants where we can recycle waste, polymer as well as metal, because metals are important in the e-waste. Like we have a gold, we have a silver, we have copper, tin, everything is there in the e-waste. 1 ton of e-waste can give you almost 150 grams of gold and much more silver and much more. So that is the the recycling of or recovering of this precise metal is very important. And then anyway, plastic can be recovered in any form, whether we can remold the plastic, we can recover the plastic and do some other parts of the plastic, or we can make a carbon out of it. So these are the two things we are working on that. Then Iot sensors. See, till date, there are no center of excellence on sensors. Now, our Trichur laboratory has that. So we can make all kind of sensors through the materials. See, now today's all technologies are material dependent. Whether you take any kind of device, or you can take any the production facility where the enhancement in the production of any chemical product where we require the catalyst, so they are dependent on some materials. So everywhere materials are very important. So the development in materials for novel applications is always a challenge. Apart from Iot sensor, now two centers already we have established. One is quantum materials and quantum technology, where we have sanctioned now. So we are going to have we are going to produce some quantum materials and for different applications. At the same time, we have a good graphene center. Has also the National Graphene Center has come in the Trichur laboratory, where we are making graphenes. We can produce graphenes in large scale, and we can make all kind of devices, all kind of applications to the graphene, which contains sensor, which can have the displays, all kind of things we produce. We have demonstrated. We have shown that all other applications we can do this graphene with some different kind of doping and all these things. And here also 50% the contribution is from the industry. So industry is going to work on these applications. So this is our R&D program. We work on nanomaterials and devices. It's a very good big unit we have. Then integrated electronic packaging. So anything we do, any device we can do, the device contain a lot of the lot many circuits and all these things. So substrate circuits and then multi-layer circuits, it has to be joined together and packed nice in very dust-free room and very in the clean room. So we have 2,000 to 2,500 square feet clean room, and there in this clean room, we make these the devices, that is packaging devices for electronic packaging of these devices. We do. We also help ISRO and DRDO for through this our facility. Then in Trichur we have piezo sensors and actuators. So all kind of ceramics where these sensors, ceramic-based sensor we do. Then we have materials for renewable energy where we work on solar cells, then hydrogen, then fuel cell, then hydrogen storage materials like batteries, then supercapacitors, all things we do here, and this is distributed in the Trichur and Hyderabad, Trichur and Pune. Then ultra high purity metals, I told you, in Hyderabad we do all kind of nanometals, or the high purity metals of 5N to almost 12 N purity. Then we have ROHS restricted hazardous testing facility in Hyderabad. We do all kind of electronic component testing and all these things. This also a self-sufficient center, which we there are some services we on chargeable basis. And in Pune, we have LTCC packaging, nanostructure materials, renewable energy, where hydrogen generation, thin film solar cell, dye-sensitive solar cell. In energy storage, we lithium-ion battery materials, sodium-ion battery and materials, flexible batteries, metal air batteries. In sensors, we have gas sensor, LTCC-based pressure sensors and magnetic sensor. NPK sensors is very important today now. Then materials for static sector like thermoelectric materials for BRC and other people we are doing, because here we work on Seebeck effect and allows Peltier effect, where a cooling effect as well as energy generation effect, where we can generate the energy through the waste heat and giving the voltage to the material, we have cooling effect. So it's very important that this kind of properties, the two properties, using these two properties, whether we can have so many other applications, and all kind of radiation setting materials we do. So research innovation to almost industry, some prototyping as well as services to industry we do. We produce, we have PhD students on different areas, work on high advanced research, and as well as group working on material development for so many applications. And whatever maybe industry requires, wherever required, we the services, small problems of the industry can solve through the consultancy or the services for 6 months, 7 months, where scientists go there, or they sponsor the projects. We have so many projects from the industries. Let me tell you about our Center of Excellence in Rechargeable Battery, where we do all kind of materials. So for the batteries, so whether it's sodium-ion battery or potassium-ion battery, metal air batteries, aluminum air, or the new batteries like advanced batteries like solid-state batteries, where the electrolyte is a polymer, ceramic, or glass. So we are our research team is also working on that, whether we can have the solid-state batteries, because that batteries can be charged fast later on, and our current problem can be solved. So current problem of vehicle is the charging time of the e-vehicle has to be reduced, because in the current technology, electrolyte used is the organic electrolyte. The anode is again the graphite or any other carbon. We use layer structured carbon, and cathode we can use the lithium cobalt oxide or nickel oxide, or all kind of other. There are many, like now people are talking about silicon can be used, porosilicon can be used for these applications. Today, the current we cannot charge the batteries fast because of the electrolyte, organic electrolyte which we used. If we replace with some very stable electrolyte, then batteries can be charged fast. So I think it's a very simple mechanism. Everybody knows about it. Like when any battery, we need the anode and cathode and one electrolyte. Okay. So the transport of ions and accumulation of ions at the electrodes while charging and discharging is very important. The storage of the ions in the cathode and storage of the ions in the anode so is important. So layer structures are very important in these two materials, because any battery is again material dependent technology. So any impurities in anode, any impurities in cathode, they are inorganic materials. Or electrolyte, if you have an electrolyte is not pure or water is there, then it will put some obstacle for transferring the ions from cathode to anode and anode to cathode by charging. So there are many things involved in this technology. So these are very high skilled technologies where we have to be very careful about the materials. Then nanostructuring in the cathode and nanostructuring in the anode also helps a lot by efficiency wise. So in this Center of Excellence, we have proposed 3 modules. These 3 modules will help to the industry or any entrepreneur or any startup. Module 1 is somebody can make the materials. These materials, anode and cathode materials, they can make. Then we can have the technology of these materials. Second module is electrode. Only you can make the electrode, means coat the electrode material on the aluminum and copper fine, which is required as an electrode. And we can make such a roll and sell it. So that is another technology. Third module is the cell assembly. You can have you can take this coated electrodes and make cathode. Then on the anode electrode we can have electrolyte and we can have a cathode electrode and assemble it. And then stacking of the single cells in the number of for the required voltage or required current you can do. So any kind of battery you can make when you have a single cell fabrication technology. So somebody can have 2 in 1 or 3. He can take and start the production. So we are here to help all this kind of those who are interested in this thing. So now all we have state-of-art materials characterization. So state-of-art from the spectroscopy to the scanning electron microscopy, transmission electron microscopy. Now we are having the XPS and all these things. So then cell fabrication facility, we have testing facility, which are application. So this is one of the things we do in the everything is available in the laboratory. Now we can make a stack of 2-wheeler also for 48-volt battery and all these things. We can also make mobile cells in our premises. So we have materials of cathode anode. Then with our materials, we made mobile battery, our own indigenous mobile battery. And this is a stack of 48 voltage battery where we also run our own vehicle on this our battery. So you can see This will show you that how this battery works. You see the power of the battery is also right. Then center of excellence in additive manufacturing. You see, additive manufacturing is very, very important for the like electronic component, which we are now proposing here is the antennas and small antennas and small circuits or substrates for electronic application. Then we can make the printable batteries. You know, in battery, the designs are very important, cathode and anode. But suppose we have such kind of layer structure, we design through this computer and then code the electrode material and on the substrate. Then definitely we can have a 3D printed batteries through the 3D printed electrode, and this stacking also can be done with this 3D printing. So very in a small packed device, we may have a large energy storage. That is one of the advantages. Then we can go to the hydrogen. So hydrogen is very, very important. So now DST has very good project, very good mission on the hydrogen, because now we are looking for looking ahead for 20 years, and we see that hydrogen has a potential, because hydrogen is a very energy rich material where we can utilize a very small amount of hydrogen with a large amount of energy. So now you can see, you might have seen that the hydrogen is the input for the fuel cell. The fuel cell technology, SOFC, is already matured. You can see in Japan, most of the buses on the hydrogen, the fuel cell, because the hydrogen utilized, they have a production plant of hydrogen and they use hydrogen for this. Today, the hydrogen problem is the cost of the hydrogen. So we need to work on reduce the cost of hydrogen, at least below the fossil fuel. Then hydrogen will flourish in fuel cell, or we can have a hydrogen engine. We can use hydrogen for small components. We can use in hydrogen for the electricity anywhere in the rural areas. All kind of things is possible with this hydrogen, if you have a cheaper hydrogen. What is the today's technology for hydrogen production? Methane steam reforming of methane is the very standard process today. But the disadvantage of this process is we get carbon dioxide and hydrogen. If you want to separate it out this hydrogen, then it is again it add the cost, and the water maybe hydrogen we are getting from the steam reforming method is not it's not cheaper. It's highly it's costly. Then hydrogen from biomass. So the technology still is not matured, but we get here also hydrogen and carbon dioxide, and this hydrogen and carbon dioxide separation, again the problem. Problem is the technology is not very efficient for separation technology. Electrolysis of water. It is very standard method in hospitals and everywhere people are using that. They are just electrolyze water. A lot of energy has to be given for this electrolysis, maybe 15 volt, 20 volts. No? So as we increase the voltage, we get the hydrogen production. Very pure hydrogen we get is, but cost of the hydrogen is too expensive to this electrolysis. Then we look for other sources where we get the hydrogen, cheaper hydrogen, because cheaper hydrogen is the mission where then we can the utilization of hydrogen for variety of application definitely is possible. So if you see the refineries, then in the refineries almost we get 7 to 10% of H2S in the refineries. Whether we can utilize that H2S and produce hydrogen and sulfur. Now what we are doing? We are just oxidizing H2S. and we are getting liquid sulfur, which we are producing for our agriculture purpose. So all these agriculture fertilizers, means all kind of fertilizers, we need the sulfur. So this will be useful. And also in the pharmaceutical, they need sulfur for the food grade sulfur. So we produce through this. But he's again a very energy incentive process. You see that nickel aluminum catalyst at 20 to 40 atmosphere, 730 to 86 degrees centigrade, 70, 86 degrees centigrade. We are running this reactor. And here also what happens, it's highly corrosive system, because you get a liquid sulfur. If any sulfur is contact with the metal and other polymers, it reacts with polymers also. So it's highly corrosive, and so every year we have to have a lot of maintenance for this kind of plants. So we are looking for whether we can generate some hydrogen and sulfur from the H2S, because if you see the formation energy of delta G here is 33.44 kilojoules. It's not high as compared to water. Water is a source where it's free water is available, or whether we can use the seawater and we can convert hydrogen from the seawater. So that is the topic of research today. People are talking, we're focusing, because see, water required the total the energy, you can see 237.19 kilojoules per mole. So a lot of energy is required to decompose H2O as compared to H2. So we are concentrating on H2O and H2S, whether we can work on it. So we are concentrating on photocatalytic process. Photocatalytic process is very simple process, because it's not like normal catalytic process. Normal catalytic process, what happens is where the active sites are important. But in photocatalytic process, it's actually electronic phenomena. When it's a photon base, so how much photons can be absorbed and how much electrons holes can be generated. Because electrons and holes are taking part in the reaction, not other things. So we need to find out that, suppose I want to do photocatalysis in UV light. So I should have a semiconductor which can have the band gap within the band gap in the UV region, so that it can absorb maximum UV and produce maximum charge carriers, like maximum the electron and hole pairs. Photocatalysis in visible light. Suppose you have you can have the semiconductors or semiconductor sulfide, oxide, or metal semiconductors, where the band gap should be in the visible region, like 3.3 electron volt to 3.2 to almost 1.7 electron volt. So we can it can take up a whole spectrum of the sunlight. And so it is always a challenge to how to tune the band gap in the visible region. You may have a lot of TiO2, ZNO, or other semiconductors. They have a band gap in the visible UV region. We need to modify them, or whether we can have the anionic doping or cationic doping in this. So this thing can be or the nanostructuring of, because nanostructuring really helps in electronic phenomena, because you see that the surface areas get increased and maximum sunlight can be absorbed, and the photo excitation is very easy in the nanostructuring material. Like you can see the size quantization effect in the is much more efficient then it will really help in this photocatalysis. So it's a simple water splitting process where you can see it's a simple photocatalyst which absorbs sunlight, produce electron holes. The H2O splitting is the decomposition, or it is a reduction process, not is the oxidation process. Now, this is the auto oxidation, reduction oxidation process. So what we have to do, we have to trap the holes, and free electron has to be there during the process. So the suppression of electron hole recombination is very, very important. So during this process, how to suppress or how to reduce the electron hole recombination? We cannot stop electron hole recombination 100% because it is a process. It's a process that when photons the light falls on the semiconductor, electron holes are generated. Okay. It's going from what electron is going from valence band to conduction band, leaving holes at the valence bond, and again electron release the energy and comes to the valence band. So it is a process, continuous process. Recombination is a continuous process in the semiconductor. We have to stop that process, and we need to have free electrons and free holes during the process, and that is really help in the water splitting. Then we get water. The reduction of water, or you can say water splitting or H2O splitting. Both the things it is possible. And this is the mechanism, is a well-known mechanism. You see when in the reduction process, electron is there, and this electron is released, and the electron gets hydrogen here with this. This is a very simple process in the photocatalysis. So what is the criteria for hydrogen photocatalysis? So it should be inexpensive, high chemical stability, because repeatability of the hydrogen production. Then same catalyst can be utilized for number of times. That is very important. So that will reduce the cost, and we get very cheaper hydrogen. So what we need, as I told you, that what we need, we would like to we would like to tune the band gap of the semiconductor in the visible region. Then what strategy we would do, that anionic and cationic doping in the existing UV light based material, then transitional elements doping, then noble metal loading, or fourth is the phase pure compound. Totally you make a new compound which has a band gap in the visible region. So a lot of things is required to do in this area. A lot of research has to be done so that we can get, because till today we do not have the process of water splitting and by photocatalytic process or photocatalyst which can produce large hydrogen production. We still need to work on on this in this area, so that at least we get quantum efficiency up to 25%, so that we will get very cheaper hydrogen. This is our setup. We produce at laboratory, as well as we have pilot plants at the top of the laboratory where we use natural sunlight. This is a very, as I told you, one of the option is a very phase pure compound. Phase pure compound means it's a combination of two. It is a ternary chalcogenide system. Okay. We can have cadmium, lanthanum, and sulfur together, and we have made a phase pure compound. And such kind of structures is very it's a highly crystalline nanostructure, you see. And we found that this has given very good photocatalytic activity, hydrogen evolution rate, almost 2000 micromole per hour, or I can say it is almost 200 ml per hour to this reactor. Then synthesis of end of ZnW4. See, ZnW4 is a highly stable material, highly stable material. We cannot, the decomposition is very high. Then it's water, the stability in water is also good, but it's UV active. ZnW4 is UV active. Then what we thought that whether we can make a nanostructure of ZnW4 and whether we can take this ZnW4 in the visible region with modify with nitrogen doping. The beauty of nitrogen doping is that small amount of nitrogen is just replaced with this oxygen, and this ZnW4, the band gap is changes from the UV region to visible region. You see here is the UV visible spectra. You see initially ZnW4 has absorbed 375 nanometer. When we dope with nitrogen, with the nitrogen content, you can see that there is a change in the absorption to the visible region. So it's very, very important. And then the same ZnW4 can absorb visible light in bigger way. So this is ZnW4 nanorods, and with nitrogen doping, we found that there is a porous structure is found. These nanorods of 50 nanometer diameter nanorods. You see these small holes here, white spot. They are the a small perforation to the nanorods, and that also helps for the production of hydrogen. And here you see how this nitrogen doping has increased a lot. Nitrogen doping gave the enhancement in the hydrogen evolution. See, NB2O5 is also a very good photocatalyst. This NB2O5, the band gap is in a visible region. Here also we dope with the nitrogen. And with the nitrogen doping, you can see here absorption in the visible region. Up to 600 nanometer, we can have these, see, from 300, 400 nanometers to 600 enhancement in the absorption, and stability of the material is highly good stability is observed when we dope with nitrogen. And beauty of this nitrogen doping is whenever we are doping with nitrogen, we found that there is a formation of modification of surface, means surface becomes little porous, and that helps a lot for the absorption of light as well as contact of water. So that helps a lot in enhancing the hydrogen evolution. Like we did water splitting, we get almost 4,320 micromole. Same with the H2S is bigger, it's much larger, 99.98. As I told you, thermodynamics for water splitting and thermodynamics H2S splitting is entirely different. Then SN3O4. SN3O4 is a good photocatalyst, and it's again in the UV region. We thought that whether we can dope with nitrogen and see whether we can make the SN3O4 porous and have the good photocatalytic activity. And we found here, you see, it's a plate like SN3O4. When we dope with nitrogen, we get the highly crystalline nanoplates, which helps a lot for producing hydrogen, enhancing the hydrogen evolution. You see that 1% nitrogen, almost 4% of nitrogen in the SN3O4 give good photocatalytic activity as compared to other, because as we increase again the further nitrogen doping and the SN3O4, again we found that there's a shielding effect observed in the material, so that the absorption of the light get reduced because of high nitrogen content, and because there is most of the nitrogen going in the lattice, but after some time this it also cover the surface, and that kind of situation will reduce the absorption of the light, and we get the lower water splitting. So this water splitting, we would like to work on more how we can enhance the spectrum, the intensity of this, much more intensity of this absorption with some other kind of group. So whether we can do anionic as well as cationic doping together. Then TON, tantalum oxynitride. Similar to NB2 niobium, we also worked on tantalum oxynitride. And tantalum oxynitride, you can see, as I told you last time, see intensity, see the absorption here, intensity, and here is almost, absorption is almost 7% or 8%, but it again, it is very similar when you shift to the visible region also. So that intensity is very important. So this is a complete oxynitride formation really helps in getting good hydrogen production. You see here almost 5,000 to 6,000 micromole with only for 0.1 gram of tantalum oxynitride gives good hydrogen production. Then initially we tried MOS2 and we produced a very single layer and monolayer MOS2 and bilayer MOS2. It's honeycomb-like structure. You see, it's very honeycomb style like to the hydrothermal reactor. See, we explain this in this paper. It's how this honeycomb structure formation takes place during the reaction. See, this hexagonal formation, hexagonal plates are formed initially, and we have first one-dimensional growth. After saturation, what happens? This one-dimensional growth again becomes accelerate the two-dimensional growth, and this the vertical growth of plates also get initiated, and we get this kind of structure. Then MOS2, we thought that MOS2 is a good product, like cadmium sulfide is a good photocatalyst. Whether we can have a very single phase compound of cadmium molybdenum sulfide, and he helped a lot because the band gap we could tune into visible region in efficient way, and we found that we get good hydrogen evolution for the cadmium indium. You can the MOS2 1452 cadmium MOS2 is 1600 micromole, and for H2S splitting it is much more. It is around 25,445 micromole. The H2S splitting gave good generally gives good photocatalytic activity in sulfide kind of semiconductors, which we observe. Then we have a MOS2 already with us, and then whether we can make a core shell. So MOS2 in the core and CDS in the shell side, so that there is the sensitization through the CDS and the electronic phenomena or whole recombination and whole electron transport through the MOS2, whether it is possible. So we did that, and we found that core shell hits can also give the good photocatalytic activity. Then same thing we did with ZnWO4. We during the in situ things, we produced ZnWO4, and we have decorated ZnWO4 with CDS. So cadmium sulfide is decorated on the ZnWO4, and that also worked well. Like nanorods are coated ZnWO4 nanorods are coated with small tiny particles, nanoparticles around 10 to 15 nanometer of CDS. We are decorated on the nanorod, which help a lot for enhancement in the hydrogen production. So this kind of flowers like kind of structure is better, like it's marigold structure. We in our one advanced material paper we have specifically published, that means published, written that how these petals kind of structure form, and then how these petals are aligned and form the flower-like structure. Because these structures are quite porous. You see, from though it shapes you see then the micron, but their petals are very thin, few nanometer thickness petals. And see, one petal may have 500 nanometer length, or 600 nanometer length, or 1 micron length, but thickness is 1 nanometer, 2 nanometer, 3 nanometer. So the aspect ratio is highly is much higher in this case. So this aspect ratio really help in giving the more surface area for the reactions. So we produce zinc indium sulfide and decorated with these petals are decorated with the SiO2. You can see these, all these petals are though the structure is retained, but these all petals are decorated with SiO2, and it helped a lot for getting enhancement in hydrogen. Then same way we do SNS decoration on the Zn and S4. We found that there is a Zn ion to S4 plate, kind of plate, and in between there is a SNS plate. So there is a one SNS plate is sandwiched between the two Zn ion to S4. It's very beautiful structure we observe for this, and very see, because of this sandwich nature of SNS, what we observe that the electron transport, or we can say the recombination of the suppression of the recombination of the electron hole pairs, it's much higher in this case because of this uniqueness of structure. We found it's a great enhancement in the hydrogen production we can, if we have with SNS decoration. Then we also work on some organic photocatalyst. See, organic, the important beauty of organic material is we can synthesize all kind of molecules. See, any dye or any colorful dye we can manufacture in the, or we can design and we can produce in the organic molecules. Okay, so in the organic molecules, if we have a semiconducting particles of TiO2, then we found that it really helps us, because this is a pentacene quinone, 60 pentacene quinone is a layer structure. You can see all kind of layers. If you see the FESM, these are the layers. In these layers, if you have this TiO2 coupled TiO2 nanoparticles and sandwich in between the two, then it helps a lot for suppression of the electron holes, recombination, and that really helped a lot. We got 36,456 micromole per hour. It's huge amount of hydrogen, but being organic, the stability we found is much less as compared to inorganic material. So we really work on this again to how we can enhance the stability with modification of the molecules. So it's very important. See, this is this is again the I have taken from the internet. This is cadmium selenide nanoparticles from 2 nanometer quantum dot 2 nanometers to 6.5 nanometers. So any quantum dots we say, when the quantum dots, when we can have the particle size of the materials close to the ionic size of that material. Like cadmium selenide has the ionic size is around 5.6 nanometer. Bohr radius is 5.6 nanometer. Yeah. So due to this Bohr radius, when all the sizes are very close to that Bohr radius, we can say that it's quantum. It's a quantum dots. So if it is a 5.6 nanometer is the Bohr radius, then 1 to 10 nanometer size will really help. This quantum dots really help in the enhancement in the optical properties. You can see that 2 nanometer, 2.5 nanometer changes, all these color changes from blue to all 7 colors we have with these particles. These are the quantum dots, right? So basically people are not talking about this, whether we can have displays out of it, because color displays, using these quantum dots. So now technology is already came in the market with these quantum dots of these semiconductors. But in what we do now, see any quantum dots, their stability is very less. Like suppose you have a cadmium sulfide as 2.5 nanometer, you cannot next day or when after a week you can if you measure the size, the size changes with the time. So there is accumulation of particles together, 1 nanometer, 2 nanometer together. They come together and form bigger particles day by day. Whether we can isolate them, and they are amorphous in nature. More or 2.5 nanometer or 3 nanometer particles, they are very, very amorphous in nature. You see there, when you have cadmium sulfide as 5 nanometer, 10 nanometer, you see the very broad XRD of this, because amorphosity is much more in these materials. So what we thought that whether glass is amorphous, in this amorphous glass, we can have this CDS quantum dots, CDCC quantum dots, bismuth sulfide. So we could take almost 10 to 12 years to develop this technique, and we are growing any kind of quantum dots in the glasses. This is the glass nanocomposite with CDS quantum dot, cadmium sulfide quantum dot. You can see initially in the glass, if there is no growth of crystal, then it is a 350 nanometer. When you grow cadmium sulfide in the glass, embedded in the glass, then their absorption is the visible region, band gap coming up to close to the 2.48 electron holes, which is of the CDS band. This very unique, so in situ growth of CDS is very important. So we can tune band that from 3.12 electron volt to 2.48 electron volt with growing CDS size here. See isolated particle here, one quantum dot of 2.5 nanometer, 2.5 angstrom. You see, if you see the SCAD pattern, very bright ring you can observe, it indicates that though the size is very, very less of quantum dots, they are highly crystalline. So that is very important in our case. Considering the quantum dots, the size quantization in glasses also, we thought that whether we can make use of this as a photocatalyst. And we found that the hydrogen evolution is much better in wherever there is a small size of quantum dots, 3 to 4 nanometers. As the size of the quantum dot increases, there is a little change in there is a little decrease in the hydrogen production. Similar trend is observed in CDS SC nanoparticles. You see, in CDS SC with size quantization, we can have yellow color, dark red, blue color, and very, very, very dark. With size increasing size, we go towards the very dark red color. So the size is the band gap is changed with the size of the CDCC, and here in the CDCC of 4.5 nanometer, you can see very, very isolated particles. You can see quantum dots of 4 to 5 nanometers, and you see the ED pattern is much crystalline. So it shows much good crystalline. This is again isolated particle quantum dot of 5 nanometer. They are very sharp. It shows that the sharp transmission spectra. It indicates that the size of the quantum dots are quite uniform. This again the UV clearly showed. Then CDCC quantum dots in some silica glass matrix, which we observed that in large scale. We observe that there is a good photocatalytic activity. We get amount of hydrogen. You see 6,850, which is only 2,000 micromole in case of we have isolated quantum dots without glass. Then we also doped CDSC CDSC growth in the glass. And we see here, you can see the TM picture of 4 to 6 nanometer quantum dots in the glass. It's very uniformly distributed, and glass is very transparent. You see, 80% transmittance, though there are many quantum dots are there in the glasses, and they are very sharp. This transmission is very sharp because the cutoff is very sharp, because the quantum dot size is uniform, almost uniform. Then we tried again, instead of silicate, whether we thought that we can change the glass type, like instead of silicate, we can use germanate glass. And we found that germanate glass can be melted at low temperature, and the growth of cadmium sulfide is much higher in the CDS. Here you can see the band gap, the absorption changes from 300 nanometers to almost 500 nanometers through this at high, very low temperature and 450 degrees centigrade. And XRD clearly shows the cadmium sulfide quantum dots formation. Very beautiful, very unique things we observe in this yet. We get orthorhombic cadmium sulfide quantum dots in this. Orthorhombic cadmium sulfide is metastable, is a metastable state. It is not stable, but in the glass it is stable, and is very, very useful for the solar cell application. See, if you in silicate glass, cadmium sulfide can grow up to 5 nanometer, but in germanate glass, it can go up to 12, 14 nanometer. That is the advantage of low temperature glass, where the crystallization spectrum, growth spectrum is much higher. So then we use for hydrogen. It's much more hydrogen, enhanced hydrogen is observed with this glass. Then we use also CDSC. You see spectrum of the band absorption spectrum from 300 to 700 with the size effect. Again, it is a size effect. With the size in the same glass, we can have all kind of. Initially, this black glass is a transparent glass, though it shows black because of quantum dots. You see, it is almost 60% transmittance. Then Raman XRD also shows a very small amount of CDCC, because because of very small amount of CDCC, they are very weak peak. And band gap you see 3.6 to 1.80. We can tune. See, CDCC band gap, CDCC quantum dot size is around 4 to 6 nanometers here again. And Raman clearly shows the formation of CDCC. And see here, generation of the hydrogen is much higher as compared to CDS, because the band gap range is up to 1.7 electron volt. Then we also have bismuth in the glass, and you see the absorption is from 600 nano towards the higher region. Okay, when we have quantum dots in it. This is without quantum dots, and after the growth of quantum dots, we can see that there is a huge shift in the visible region, and that helped a lot for hydrogen evolution. The Raman we have taken because Raman clearly shows the formation of bismuth in the glass. TM clearly shows that a very tiny nanoparticles of 4 to 5 nanometers of bismuth is, you can see here, very uniformly distributed in the glass. And we observe that is a much higher hydrogen evolution, 11,540 for this hydrogen, for these bismuth nanoparticles. Smaller is the particle in the glass, the higher is the hydrogen evolution, which we observe. And it's a repeated. Then another compound we recently developed is the Ag3O4. Ag3O4 is highly good, sensitive to the sunlight, because visible light, and when you have Ag3O4 particles on under natural sunlight, you see that the Ag3O4 is not stable. Yeah, after some time, you find that Ag3O4 get decomposed into phosphoric acid and silver oxide. So this kind of thing happen when it's a highly photocorrosive system. So considering that, whether we thought that whether these Ag3O4 nanoparticles can be grown in the phosphate glass and see their stability, and exactly we found that the Ag3O4 is highly stable in the glass, and we can, if you see the structure of Ag3O4, it's a highly intense dodecahedrons of we can observe, and similar very small tiny dodecahedrons are also observed in the glass. You can see with color changes, means there is a change in the size. And this is a Raman Spectra, shows the formation of Ag3O4 in the glass. And see here, all these nanoparticles very clearly shows that they are highly crystalline. Also, they are highly crystalline also. And this is actually Ag3O4 spectra of powder of Ag3O4, which we utilize for the formation of glass. And this is the spectra. You see, there is a very long absorption in the visible region. This is a small peak between 300 to 400 is because of dissociated silver in the glass. Whenever it might decompose during the glass formation and get. And then hydrogen production. With good hydrogen production, we have a small amount of the small size of Ag3O4 is there in the glass. Then we produce large quantities of glass composite for our different applications. And this is a very highly intense. You can see very uniform quantum dots. Then we produce, we also run pilot plant with this hydrogen production of this using our glass system. And we produce hydrogen 45,000 micromole per hour. It's almost 2 liters per hour hydrogen evolution observed when we can use cadmium cellular quantum dot glass nanosystems. Interestingly, what we found that when CDSC we doped in the glass and we we change the thermal system, thermal processing from very prolonged thermal treatment. We observed that this 5 nanometer CDSC nanoparticles get aligned and form nanowires. That's very interesting thing we observe, and we are thinking that how we can utilize this for. So, though you said the transmittance is almost 82%. So nanostructuring in the glasses and their wires, their formation of wire inside will really help in some photonic properties. Then recently we also grown MOS2 nanoparticles in the glasses. You see here MOS2, very interesting. You see MOS2 is a plate-like structure. So you see in the MOS2 glass itself, you get the plates of MOS2. Very interesting. We are not applied, we have not done any other applications, but now we are going to see what kind of applications we can have with this. With the glass, though the glass is very transparent. So using the photocatalytic technique, we found that whether we can also purify water. So when some of the glasses can be made of quantum dot size, quantum dot based glasses, which can cover the whole spectrum from UV to almost near IR. They can absorb the sunlight, and whether the water can be boiled, and this the energy can be transferred to the water, and water can be boiled, and this water can be filtered, and purified water can be possible at in the natural sunlight. So we are very close to this now, and we are getting 80 degrees temperature with some of the quantum dots, and now we can see that how we can coat to the glass reactor. We have the powder of these quantum dots. We are coating to the glass, or whether we can have the substrate, and on the substrate we can coat, and we can have a beads, and on that kind of study is not going on with Royal. This project is under the Royal Society of Chemistry, because since it's a water purification is a very societal type of project. So we are in the collaboration with University of Leeds with this project. So I have covered all kind of nanostructures. Only one applications we have to, because it is not possible to tell you now all other applications of nanostructures. So I just concentrated about our 10% of work on the hydrogen I have presented here, where I have just explained about zinc and sulfide cadmium nanostructures. It's a hierarchical nanostructures, then doped structure, nitrogen doping, how it is possible to have porous semiconductors to the nitrogen doping. Then new approaches like quantum dots in glasses, Ag3O4 is the new things which we have developed, which have good potential in water splitting as well as water purification. Because of Ag3O4 nature, we found that the pathogen, the killing of pathogen is possible through this Ag3O4. We tried some experiments, and we found that the E. coli, we tried on E. coli, and we found that under natural sunlight, the concentration of E. coli has been drastically reduced within 1 and 2 hours with this Ag3O4 glass. Then we are also talking about MOH2 glass, whether we can use same for that water purification. So there are many other applications of these glasses, quantum dot glasses, including from water purification to hydrogen to photonics, so where we need a large spectrum of band gaps. So there we can work on this material. Thank you very much, and I think I have covered almost things from battery to some hydrogen, because both are important today. So today there are two important things. Hydrogen, we have energy generation system and energy storage system. Energy storage system, we have energy generation system, solar cell people are working, fuel cell people are working. But this energy has to be stored somewhere and utilized whenever you require. No? So energy storage devices are also very important. We have only two energy devices, energy storage devices. One is supercapacitor, one is battery. Battery has higher energy density, low power density. Supercapacitor is the higher power density, low energy density. Whether we can make combination. So a lot of things are going on now. So whether we can run the buses, whether we can on this supercapacitor through battery combination. Okay. So these things are going on, and our Center of Excellence definitely will definitely working in that direction. Whether we can combine together and we can have a very moderate power density and higher energy density. Thank you very much.
So thank you very much, sir, for this wonderful talk. And this talk will be very, very beneficial for us, not only for students and research scholars, but also for our faculty members of the department. And it is a very, very informative talk for all of us. So respected speaker started with the introduction of the three center of excellence. One is in Pune, which is for rechargeable batteries and technology and 3D printing. Second in Thrissur for IoT sensors, and third in Hyderabad for e-waste recycling and management. Then he talked about the R&D program of the centers, which are like nanomaterials and the devices, integrating electronics packaging, materials for renewable energies, ultra high purity materials and semiconductors. Then he talked about the importance of the layered structures and nanostructurings of the materials for electrode materials, materials for electrodes for the rechargeable batteries technology. And then he talked about the 3D printing electrode for lithium-ion batteries. And then he touch upon the hydrogen generation technologies like hydrogen from biomass, electrocatalysis from water, utilization of H2S for the hydrogen generation. Then he talked about the hydrogen by photocatalysis in details and various key factors for the water splittings, which are very, very important. He talked about the tuning of the band gap in visible regions, sulfide, using the sulfide semiconductors, oxide semiconductors, and nanostructuring the materials. These are the very important factors for the efficient photocatalysis. And the criteria for these photocatalysts has been also discussed by the speaker, which should be like inexpensive materials. They should be inexpensive, non-toxic, high chemical stability should be there, absorption in the visible light, and the stable towards the photocorrosion. Then he talked about the nitrogen doped nanostructure material like zinc WO4 and SN3O4, NB2O5 materials, and he discussed that doping with nitrogen atoms can tune the absorption spectra for the photocatalysis. And then he touched upon the mono and bilayers of the MOS2 and the cadmium MOS4 material and the organic photocatalyst. And finally, he talked about the quantum dots, which are very, very important in the today's scenarios for the various applications. And cadmium sulfide doped glass nanocomposites for hydrogen generation, confinement of Ag3PO4 quantum dot into glass matrix, MOS2 quantum dot classes are the highlights of the last part of the presentation. And finally, he touched upon the water purification using this quantum dot. So, sir, this was very, very informative talk. We all enjoyed this talk. And now, finally, I would like to thank our patron of the session, Professor Tiwari sir, who is actually very busy in this foundation week various activities, so he could not attend this webinar. So I would like to thank Professor Tiwari sir, who is our motivation and driving force behind this series of the webinars. Thanks are also due to today's expected speaker, Professor Dr. B.B. Kale sir, Director General, Center for Materials for Electronics Technology, for such a wonderful talk, sir, and sparing his valuable time from his busy schedule. I also thank all the audience who are listening carefully your talk and the technical staff for the smooth functioning of this webinar. So thank you all. Thank you very much. Now, finally, at last, I would like to request you all to rise for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन